In this video, we're going to look at the fact that kernels of group homomorphisms are normal subgroups of the domain. So I want to kind of set up the basic idea. We are going to let F go from G to H be a group homomorphism throughout this particular video. Now, in the last video, we showed that the kernel of F is a subgroup of the domain, and the image of F is a subgroup of the codomain. And the question that we want to now look at is the kernel of F normal in G. And to do that, we have to actually kind of remind ourselves of a little bit of stuff about normal subgroups. So I want to recall some information about normal subgroups. The first thing is the definition of normal is that H is normal in G if and only if, and we want to get the quantifiers right here, for every element inside the group G, the left coset AH is equal to the right coset HA. But we also have a big theorem that I'm just going to call the normal subgroup theorem. And the normal subgroup theorem says that H is normal in G if and only if, for every element inside the group G, G inverse times H times G is actually equal to the subgroup H. But the condition can be weakened to read, for every G inside G, the conjugate subgroup G inverse times H times G is a subset of the subgroup H. That if we happen to have this condition, that is enough to force that H is normal in G. And it turns out that's how we're going to investigate whether or not the kernel is normal inside G. So let's now look at what about the kernel. So is the kernel normal inside G? Well, in order to look at this, what I want to do is I want to take an arbitrary element in G and look at the conjugate subgroup G inverse times the kernel of F times G. If we can show that this arbitrary conjugate subgroup G inverse times the kernel of F times G, if that is a subset of the kernel of F, then we're going to know that the kernel of F is indeed normal inside G by our normal subgroup theorem. Now, the question is, how do I show that particular set inclusion? Well, to show that, I'm going to take an arbitrary element inside the set G inverse kernel of F times G. And let me put some parentheses around that to make it clear that we are multiplying every element inside the kernel of F by G inverse on the front and G on the back. And I want to show that that arbitrary element of G inverse times the kernel times G happens to be inside the kernel of F. So that's what I want to show. Well, let's see. What am I going to do? Well, since X belongs to G inverse times the kernel of F times G, we know that there exists some K inside the kernel of F such that X is equal to G inverse times K times G. Now, one thing that I also want to point out is that I know something important here. k is inside the kernel of f says f of k is equal to EH, because you don't get into the kernel unless f sends you to the identity in the target group, and the target group is H. So now what I want to do is I want to look at what happens to x under f. In other words, I want to look at this. F of x. Well, f of x is going to be f of g inverse times k times g, because x, of course, is g inverse times k times g. Now, f itself is a homomorphism, so this statement here can be broken up into f of g inverse times f of k times f of g. And this is because f is a group homomorphism. If I want to come back here, I can say because x is equal to g inverse k g, since we started with x belongs to this guy here. Moving right along, what do we have? Well, let's see. We've already pointed out f of k is known to be EH. So I'm going to put that in right there. So we now have f of x is equal to f of g inverse times E sub h times f of g. And it's worth pointing out that this product is in H because f of g and f of g inverse belong to H, because f sends elements in G to elements in H. So what I'm going to do is I'm going to put some parentheses around this, and I'm going to recall that f of g belongs to the target group H. And so what does that say? Well, that says the group identity EH times f of g is just going to be f of g. And so that will let me rewrite my work over here as f of g inverse times f of g. That's what's justifying that step. But now f is, remember, a group homomorphism. And one of the things that we learned about group homomorphisms in one of the earlier videos is that since f is a group homomorphism, I know that f of an inverse is the inverse of the image. In other words, f of g inverse is f of g's inverse. And over here I'm looking at f of g inverse. So I can rewrite that as f of g inverse, and then we have times f of g. Now, what I want to look at here is I've got an element f of g times its inverse. And I know that any element times its inverse is just the group identity. And finally, as we've already pointed out, this element here belongs to H. It's right up there. And so this product has to be the identity in group H. So what we've now got is f of x boils down to E sub h. And what does that mean? Well, by the definition of kernel, that says x belongs to the kernel of f. And what I want to remember is that x was an element of g inverse times the kernel of f times g. In fact, this guy was an arbitrary element of that set. And so what I know is that g inverse times the kernel of f times G is a subset of the kernel of F. And now the other thing that I want to point out, and I'm going to come all the way back up to where I started making these things, is that we picked an arbitrary conjugate subgroup to start with. So what I have down here is that since G itself was an arbitrary element, arbitrary, I don't know how to spell arbitrary, and it's showing. And arbitrary. Element of G, and that looks weird. Since little g is an arbitrary element of capital G, we know that this arbitrary conjugate subgroup is always going to be a subset of the kernel. So in other words, this is going to be true for all g's inside set G, and hence that says that the kernel of F is indeed normal inside G. And that's by our normal subgroup theorem. And now the final thing, and so that completes the proof. But there is one final comment that I want to make. And so I'm just going to leave this in a different color, actually. And the comment is that the image of F, while it is a subgroup of the target set H, it may or may not be normal inside H. And what I mean by it may or may not be normal is that there are examples of group homomorphisms where the image does turn out to be normal in the target set, and there are also examples where we have group homomorphisms where it turns out that the image of F winds up not being normal inside H. We'll investigate that in some of the homework that gets assigned.